What is up, everybody? It is Mr. Holtz, and today we're going to be talking about Beer's Law. Now, in chemistry, Beer's Law is something that we use to correlate the absorbance or intensity of a color to the concentration of a solution. So what we're going to be doing today is we'll take a look at what is Beer's Law and how do you use it. We'll talk a little bit about the relationship between color and absorbency of different wavelengths of light in certain solutions, and we'll also go through looking at an experiment that incorporates Beer's Law and something that we would be doing if we were in class this semester. So let's dive into it. Okay, so what is Beer's Law? Well, before we get to Beer's Law, let's talk a little bit about solution concentration. So as you might know, when something's more concentrated, it usually has more of something in it. So if you've ever made lemonade, obviously if you make a glass of lemonade with 1 scoop of lemonade, it wouldn't be as concentrated as if you made a glass of lemonade with 2 scoops of the lemonade powder. So what we have here is a picture of, it doesn't really matter what it is. I don't actually know what's in these. Could be beet juice, could be, not really sure. Could be Kool-Aid. But what we have here is some dilute solutions where there's not a lot mixed in. Okay, so you could imagine like 1 drop of food coloring in this big glass of water. Whereas as we move to the right, the solutions get more and more concentrated, and we can tell that because the colors get darker and darker. Now, there are going to be points in chemistry where you have 2 solutions that might look like these 2 in the middle, right? They're pretty similar. You might be able to tell that the one on the right's a little bit darker, but they're pretty close. And that happens a lot in chemistry. So Beer's Law is an equation that we can use where if we have enough data already, we could take either of these solutions, run it through a spectrometer, which we'll look at in a minute, which is the machine that we use to study the absorbance and intensity of different solutions. And you could determine exactly what the concentration of this solution is versus the other solution. So it's helpful in chemistry if you're looking at 2 different solutions and you can't tell which one's more concentrated, or if you're looking at a solution of an unknown concentration and you're thinking, how in the world can I figure out what the concentration of this solution is if I don't know how much stuff was added to it? Well, let's dive into that in a minute. Before we get to that, let's talk a little bit about colors. So here we have a color wheel, and hopefully you guys have seen this before. Now, if you didn't already know, there's some interesting interactions between different wavelengths of light, their amounts of energy, their wavelength, and their frequency, which we've talked about earlier this year. And what we're going to be talking about today is what kinds of wavelengths of light do different colors absorb, okay? So here, obviously, our solution is somewhere from a light pink to a dark red, which would be around here in the red section of our color wheel. Now, in terms of the light that is absorbed and light that is emitted, these look red because they're emitting red light, right? We are picking up the light that is red with our eyes. That's why we think of these as red. Now, what does that mean about the light that's actually being absorbed? Well, this means that generally, the light of opposite color is what is being absorbed, because obviously this isn't blue or green or yellow because those wavelengths of light are being absorbed by this solution. Now, the most intense will be the opposite of the color that we're seeing. So obviously here for red, the wavelength that's being absorbed the most by these solutions is what would be the opposite, which obviously here, based on this color wheel, is green, okay? So you can imagine if we had something that was blue, it would be really good at absorbing orange light. If we had something that was violet or a purplish color, that would be really good at absorbing yellow light because it's the opposite, okay? And we would be seeing all of the violet or the purple light that's actually being emitted from that object. Now here is a wavelength basis for these different kinds of colors, and it shows us where the visible spectrum is with the rainbow and all the different colors in the rainbow, and where the ultraviolet and the infrared fall outside of those ranges. So we'll take a look at that in a minute. So Beer's Law, or the equation for Beer's Law, is written right here. A equals epsilon, or lowercase Greek epsilon, times L times C. Okay, so what are all of these? Well, A is the absorbance, so how much of the light is being absorbed, which is a value that we're going to get from the machine that we put our sample into. But notice here there's no units for absorbance, okay? So we just leave that value as is. The epsilon value refers to our molar absorptivity, and this is a constant value. So we'll look at an example here in a second. But what this means is, this is how strongly a chemical species absorbs light at a specific wavelength. So to what extent does our solution absorb different colors of light? Okay, now notice this is at a specific wavelength. So this is dependent on what actual color are we talking about here. So for example, copper sulfate, which if you dissolve it is a blue crystal, gives you kind of a light blue solution. So you would imagine that it absorbs orange light really well. Well, depending on the wavelength of light, a blue solution would absorb blue light not very well because most of that's being emitted. It would absorb orange and red light the most, and it probably wouldn't absorb green or purple light too much, but it would absorb it a little bit. Okay, so it depends on the wavelength that we're actually talking about for a specific chemical species. So in this case, the epsilon value, or our molar absorptivity constant for copper sulfate at 635 nanometers, which if we look over here, 635 nanometers is in about this orangish range. So that's the color we would expect it to absorb really well. The molar absorptivity value would be 2.81 inverse molar times inverse centimeters. Now we need the molar absorptivity units to be inverse molar, inverse centimeters because of how it comes out in the equation. Again, absorbance does not have any units. So we'll look at some examples here in a minute, but just keep that in mind for now. Okay, L, which is the next variable, is our path length. Now, based on the fact that we are using our spectrometers, which is the machine we'll see in a minute, the path length is always going to be 1 centimeter because the distance that the light travels when it exits the light bulb to where it's picked up by the receiver, the difference between that is 1 centimeter. So the cuvettes that we'll be using where we add our actual solution is 1 centimeter across, which basically just means how much of the solution, what length of a solution is that light going through? Because if it goes through 1 centimeter versus 2 centimeters, you can imagine that the solution would absorb a different amount of light if it has more distance to absorb that light in. Okay, and then our last variable here, C, lowercase letter c, is just the concentration of our solution in molar or molarity. So the molar value and the centimeter value are going to cancel out with the molar absorptivity, which give us no units, which is good because, again, absorbance has no units. So this here is our spectrometer. So this is what we would be using if we were in the lab and we were actually running different samples to collect absorbency values on certain concentrations. So right in here is where your sample would go. And if this was on and plugged in, we would have a light source coming through this little opening right here. So it would be coming out in this direction that my pen is facing. And because it has this little hole right here for a sample, this is called a cuvette. So if you have a sample, you would be adding a little bit of solution into here. It's just a little plastic container that holds some liquid. Now notice that there are ridged edges and flat edges or clear edges. So the light, you would obviously want to go through the clear edges. So I would be facing it just like this. So the light would be going through the clear edges as opposed to the ridged edges, which is the difference between the side that you're supposed to hold and the side that you're supposed to have the light go through. And on the other side, over here, there's a receiver that picks up a signal based on the amount of light that actually makes it through the solution. So you could imagine that if I was filling this cuvette here with a sample of just tap water, most of the light would make it through. So the receiver over here would pick up that most of the light made it through, and it would give you an absorbency or an intensity value based on that, and based on what you told the computer to register for. Now, if I had something like a really, really dark liquid, like maybe prune juice or something, that would probably absorb quite a bit of light. Now, obviously, it would absorb different amounts of light at different wavelengths, but when the light goes through the sample, it's picked up by the receiver, and then it sends a signal to the computer saying how much of the light was absorbed by the sample and how much of the light went through the sample. Okay, so here's our equation for Beer's law. Now, if you guys remember, L is a path length of 1 centimeter, which means we're going to be multiplying by just a value of 1 every single time we use this equation. Now, if you remember the units for molar absorptivity, you remember that it has inverse molar, inverse centimeters, which means when we multiply the path length value by 1, not much is going to happen because obviously multiplying anything by 1 is itself, but we're going to cancel out our centimeter unit, again, to make sure that our absorbance still has no units. So just for the purposes of data analysis, if you think about this, you could really rewrite the equation as absorbance equals epsilon times concentration times 1, right? So I'm just going to ignore that times 1 for now. Okay, so let's get rid of this equation up here. Now, when we're actually graphing and analyzing data from solutions that we've already tested, we generally want a linear graph. Now, if you go back to geometry or algebra or whichever class you learn this in, the formula for a line is y equals mx plus b, right? Where b is just our y-intercept. So if you correlate these two equations, I'm just going to X out this b here, then we get absorbance equals epsilon times concentration, and y equals mx, right? Obviously, b is our y-intercept, so maybe this equation can have some y-intercept with a number up here, where n is just whatever we get based on the graph. But think about what these all are. Remember, m for a linear graph is the slope, right? Which means that in a line, this is a value that does not change. So just like the slope of a line doesn't change, remember that molar absorptivity is a constant value, okay? So if this is a constant value, this is never going to change. So these two equations are correlated in that once you get a graph for your solutions, you should have an equation for your graph or for a best fit line of your graph. So for example, let's say you made 4 known solutions, okay? So you know their concentration, so you know what values go down here. Again, this would be in molarity. And you got their absorbance values by testing them in the spectrometer. Low concentration, one at a high concentration, or a medium concentration, maybe another one at a medium concentration, and one at a high concentration. So generally, and obviously this isn't going to be perfect here, but generally it gives us an equation for a line, okay? I should have done these in blue to try and go with my legend up top. So these are solutions of known concentration that you have already made and tested. So you know where they fall. So it doesn't really matter. None of this gives you any extra information, but you should be able to get a y equals mx plus b line from those data points, right? When you add your best fit line. Now, if you correlate that to absorbance equals molar absorptivity times concentration, then obviously, as we can see here, based on where I put absorbance and concentration in our axes, y is the absorbance, and that's true here. C, or x, is our concentration, which is true on this axis here, which means that the slope of our best fit line must be the molar absorptivity. So the slope is equal to that constant value, and generally that constant value is what we're looking for, because this is usually a value we don't know. But once you find that value, that means that you can fill out the equation A equals molar absorptivity times C. So if you have this value here for your molar absorptivity, you can basically find the absorbance from any concentration or the concentration from any absorbance, which means if I gave you just some random solution with some stuff in it, and I said, hey, you don't know what the concentration is of this, but I would like you to figure it out. If this solution is made up of the same stuff, for example, copper sulfate, if this solution is made up of the same stuff as the solutions you made to get this initial graph, then all you need to do is take a sample of this into the cuvette, run it through the spectrometer, and once you get your absorbance value, then you can say, okay, well, my unknown solution had an absorbance of right here. Hopefully it will fit on your line or pretty close to your line. Or you can just plug the absorbance directly into this equation. If you have the molar absorptivity, you only have one unknown value, so you can solve for your concentration. So this is the whole important point of why we use Beer's law, and it's really not that difficult as long as you have some starting solutions or some starting data points to begin with. Because if you don't have those, you won't be able to find anything about your unknown solution. So as you guys can see, I've already measured out 4 different masses of the copper sulfate, which is this solid right here. And if you look closely, it's this super pretty blue crystal. So it looks really awesome. What I've done so far is I've gotten 4 different measurements of masses. So I got about 0.24 grams, 0.5 grams, 1 gram, and a little over 2 grams. So what I'm going to do is I'm going to add these to our water, and each of these is measured out to 100 milliliters. Now, I don't have enough stir plates, so right now I've only got 2 at a time. So we'll let those dissolve for a little while. and I'll come back and get the other two. So we'll deal with these later. But before that, as you can see here, I've already done the calculations to figure out what are the concentrations of every single mixture I'm making right now. So as you guys can see, I'm using millimolar, which has a lowercase m before the molarity unit that we're used to for concentration. If you remember, molarity is moles per liter. Millimolar really means millimoles per liter. And a millimole is a thousandth of a mole, right? So milli is our prefix in the metric system for 1/1000th. So this right here is the mass for each of my samples divided by the molar mass of copper sulfate pentahydrate, which is the solid crystal that we're using. I figured out how many moles of copper sulfate I have, and since each one is being dissolved in 100 milliliters, I divided it by 0.1 liters to figure out the concentration. Now these values are going to be important for what we plug into our spreadsheet once we come up with a graph of concentration versus absorbance. So we'll need these later on. So as you guys can see here, I have a spreadsheet full of data. Now this data was gathered by actually using the spectrometer and inserting a cuvette full of all of my different samples. So as you saw, I made 4 different samples. So here's a set of data for the wavelength and what the absorbance was at each of those wavelengths. So at 416 nanometers, the absorbance of my lowest concentration solution was 0.598. The next concentration had an absorbance of 0.258 at 416 nanometers. And obviously, this goes on and on and on. Now, to actually make sense of this, I made a little graph up here. So each of these different colors represents a different concentration of solution that I have made, and the absorbance at different wavelengths for each of those solutions. Now, when we're doing Beer's law, it's really important to make sure that when we create our best fit line, we're using the absorbance values at one specific wavelength. So based on how these graphs are overlaid on each other right now, because the blue graph is my lowest concentration, I tried to pick a wavelength that showed that the absorbance increased as my concentration increased. Now, I didn't run this experiment perfectly. I could have used a better analytical balance. I wasn't very analytical about measuring the volumes. I tried to get pretty close, but I was using tap water instead of DI water because I was rushing through the experiment a little bit. So I could have ran the experiment a little better and gotten some more accurate numbers. But as you can see here, at a little bit over the 800 nanometers, I have a pretty good increase in the concentration of the solution as we go from 9 to 20 to 40 to 80. And that shows that the absorbance increases. So when I made my best fit linear graph, I ended up taking a wavelength just over 800, which is technically in the infrared range, but the spectrometer does still collect data in that range. So you can see if I scroll down, I highlighted the section, and obviously this data goes on for a while. I highlighted the section right here that I used to find the molar absorptivity specifically at 806 nanometers. Okay, so notice here, it's at 806 nanometers. Now, when you are given an unknown solution, if you are using this best fit line that I created down here, you would want to make sure that you are only using the absorbance of your unknown solution at 806 nanometers. If you use an absorbance at a different wavelength, it's going to have a different molar absorptivity. So that's something that you need to keep in mind when creating these graphs. Now, the red line is my best fit line, and it has an R squared value of 0.91. 0.99 or 1 would mean that it's perfect. So my data is obviously not perfect, but that's okay. Now, for the actual equation, the equation for my best fit line would be y equals 23.5 times x plus 2.54. So 2.54 would be my y-intercept, and the 23.5 would be our slope here, which would be our molar absorptivity. Now, like I said, that value is a little bit off, but I'm going to blame most of that on my analytical skills and seriousness of taking the measurements for this lab. But as you can see, as we increase in concentration, we increase in absorbance, and that's the whole point of Beer's law. Thank you guys so much for watching today's video. Hopefully you got something out of it and you learned something about Beer's law and spectroscopy. Go ahead and hit that like and subscribe button, and leave a comment or a question down below if you need some help or you want to see something else in the future. Thanks so much for watching.